Flow developers. Today is the third lesson, fungible tokens. In this tutorial, we're going to deploy, store, and transfer fungible tokens. To get started, we're going to open up the Flow Playground, which is linked inside of this lesson. Some of the most popular contract classes on blockchains today are fungible tokens. These contracts create homogeneous tokens that can be transferred to other users and spent as a currency, such as ERC20 tokens on Ethereum. Usually a central ledger keeps track of a user's token balances. With Cadence, we use a new resource paradigm to implement fungible tokens and avoid using a central ledger. The Flow Network Token. In Flow, the native network token will be implemented as a normal fungible token smart contract using a smart contract similar to the one in this tutorial. There will be special contracts and hooks that allow it to be used for transaction execution payments and staking, but besides that, developers and users will be able to treat it and use it just like any other token in the network. We're going to take you through these steps to get comfortable with the fungible token. 1. Deploy the fungible token contract to account 0x01. 2. Create a fungible token object and store it in your account storage. 3. Create a reference to your tokens that others can use to send you tokens. 4. Set up another account the same way. 5. Transfer tokens from one account to the other. And then 6. Use a script to read the account's balances. Before proceeding with the tutorial, we recommend that you follow the Getting Started in Hello World tutorials to learn the basics of the language in the playground. If you have not already taken those lessons, check out the previous lessons that we have also published on the Flow blockchain. Fungible tokens on the Flow emulator. First, you'll need to open the link. We've already opened the Flow Playground link for Lesson 3. Open the account 0x01 tab and see the file named exampletoken.cdc. Exampletoken.cdc should contain the full code for the fungible token, which provides the core functionality to store fungible tokens in your account and transfer to and accept tokens from other users. Okay, 0x01 has the example token smart contract, and then it's got the entire interface for implementing another fungible token. The concepts involved in implementing a fungible token in Cadence can be hard to grasp at first. For an in-depth explanation of this functionality and code, continue reading the next section. Or if you want to go immediately into deploying it and using it in the playground, you can skip to interacting with the fungible token section. So we could just skip everything and then go all the way down, but because this is a course for beginners into the blockchain coding space, we're going to go through it all to talk about what fungible tokens are and how they work in Cadence in the Flow blockchain. Fungible tokens, an in-depth exploration. How Flow implements fungible tokens is different from other programming languages. As a result, ownership is decentralized and does not rely on a central ledger. Bugs and exploits present less risk for users and less opportunity for attackers. There's no risk of integer overflow or underflow. Assets cannot be duplicated, and it is very hard for them to be lost, stolen, or destroyed. Code can be composable, rules can be immutable, and code is not unintentionally made public. Decentralizing ownership. Instead of using a central ledger system, Flow ties ownership to each account via a new paradigm for asset ownership. The example below showcases how Solidity implements fungible tokens, with only the code for storage and transferring tokens shown for brevity. So the ERC20, which is the Ethereum compliant fungible token contract, we've got a mapping with private balances, and then transfer where we've got the sender, the recipient, and the amount, and then we can send a balance from one to another. We require that the balance of the sender is greater than the amount that they're trying to send. We then subtract the amount from the sender, and then we add the amount to the recipient. As you can see, Solidity uses a central ledger system for its fungible tokens. there is one contract that manages the state of the tokens, and every time that a user wants to do anything with their tokens, they have to interact with the central ERC20 contract, calling its functions to update their balances. This contract handles access control for all functionality, implements all of its own correctness checks, and enforces rules for all of its users. Instead of using a central ledger system, Flow utilizes a few different concepts to provide better safety, security, and clarity for smart contract developers and users. In this section, we'll show how Flow's resources, interfaces, and other features are employed via a fungible token example. Intuiting ownership with resources. An important concept in Cadence is resources, which are linear types. A resource is a composite type that has its own defined fields and functions similar to a struct. The difference is that the resource objects have special rules that keep them from being copied or lost. Resources are a new paradigm for asset ownership. Instead of representing token ownership in a central ledger smart contract, each account owns a resource object in their account storage that records the number of tokens they own. This way, when users want to transact with each other, they can do so peer-to-peer without having to interact with a central token contract. To transfer tokens to each other, they call a transfer function, or something equivalent, on their own resource object and other users' resources, instead of a central transfer function. This approach simplifies access control because instead of a central contract having to check the sender of a function call, most function calls happen on resource objects stored in users' accounts, and each user controls who is able to call the functions on resources in their account. This concept, called capability-based structure or capability-based security, will be explained more in a later section. This approach also helps protect against potential bugs. In a Solidity contract with all the logic contained in a central contract, an exploit is likely to affect all users who are involved in the contract. In Cadence, if there's a bug in the resource logic, an attacker would have to exploit the bug in each token holder's account individually, which is much more complicated and time-consuming than in a centralized ledger system. Blow is an example of a resource for a fungible token vault. Every owner who owns these tokens would have this resource stored in their account. It's important to remember that each account stores only a copy of the vault resource and not a copy of the entire example token contract. So it's only a copy of the resource, not the contract. The example token contract only needs to be stored in the initial account that manages the token definitions. So we've got this time a Cadence contract instead of a Solidity smart contract. We've got a public resource called vault. It's a provider and a receiver. We've got a balance. We initialize a balance. Then we have a withdraw function and a deposit function. Instead of a transfer, we have a withdrawal and a deposit. This piece of code is for educational purpose only and is not comprehensive. However, it still showcases how a resource for a token works. Each token resource object has a balance and associated functions such as deposit and withdraw. When a user wants to use these tokens, they instantiate a zero balance copy of this resource in their account storage. The language requires that the initialization function init, which is only run once, must initialize all of the member variables. So they've got the balance and then the init. We're just zooming in on the first part. We use unsigned fixed point integers because they do not require a concept of a negative number and allow for more clear precision. Then the deposit function can be available for any account to transfer tokens to. We've then got a public function of deposit, and then we just add the balance from the from's balance, and then we destroy from. When an account wants to send tokens to a different account, the sending account calls their own withdraw function first, which subtracts tokens from their resources balance and temporarily creates a new resource object that holds this balance. The sending account then calls the recipient account's deposit function, which literally moves the resource instance to the other account, adds it to their balance, and then destroys the used resource. The resource needs to be destroyed because Cadence enforces strict rules around resource interactions. A resource can never be left hanging in a piece of code. It either needs to be explicitly destroyed or stored in an account storage. When interacting with resources, use the @ symbol and a special move operator. So, a couple things to note here. A resource can never be left hanging in a piece of code. There are two options for a resource. You either explicitly destroy it from an account, or you put it back into the account storage. When interacting with the resource, we use the @ symbol and a special move operator. So we've got the @ symbol to signify that we're working with resources. The @ symbol is required when specifying a resource type for a field, an argument, or a return value. The move operator makes it clear that when a resource is used in an assignment, parameter, or return value, it's moved to a new location, and the old location is invalidated. This ensures that the resource only ever exists in one location at a given time. If a resource is moved out of an account storage, it either needs to be moved to an account storage or explicitly destroyed. In this case, we're destroying it from the sender. This rule ensures that resources which often represent real value do not get lost because of coding error. You'll notice that the arithmetic operations aren't explicitly protected against overflow or underflow. So there's no overflow or underflow protections. In Solidity, this could be a risk for integer underflow or overflow, but Cadence has built-in overflow and underflow protection, so it's not a risk. We're also using unsigned integers in this example, so the vault's balance cannot go below 0. Additionally, the requirement that an account contains a copy of the token's resource type in its storage ensures that the funds cannot be lost by being sent to the wrong address. If an address doesn't have a correct resource type imported, the transaction will revert, ensuring that transactions sent to the wrong address are not lost. The line in withdraw that creates a new vault has a parameter named balance specified in the function call. So we create a new vault with the balance of amount. This is another feature that Cadence has to improve the clarity of code. All function calls are required to specify the name of the arguments they are sending unless the developer has specifically overridden the requirement in the function declaration. Next section, ensuring security in public, capability security. Another important feature in Cadence is its utilization of capability security. This feature ensures that while the withdrawal function is public, no one except the intended user and those they approve of can withdraw tokens from their vault. Cadence's security model ensures that objects stored in account storage can only be accessed by the account that owns them. If a user wants to give another user access to their stored objects, they can link a public capability, which is like an API that allows others to call specified functions on their objects. An account only has access to the fields and methods of an object in a different account if they own a capability to that object that explicitly allows them to access those fields and methods. Only the owner of an object can create a reference for it. Therefore, when a user creates a vault in their account, they only publish references to the deposit function in the balance. The withdraw function can remain hidden as a function that only the owner can call. As you hopefully see, this removes the need to check message.sender for access control, which is what we do in Ethereum and Solidity, because the functionality is handled by the protocol and the type checker. If you aren't the owner of an object and don't have a valid reference to it that was created by the owner, you can't access the object at all. Using interfaces to secure implementation. Thanks for sticking with me. I know this is kind of dry, but it's important to know so that you can understand what fungible tokens are about. The next important concept in Cadence is design by contract, which uses preconditions and postconditions to document and programmatically assert the change in state caused by a piece of program. These conditions are specified in interfaces that enforce rules about how types are defined and behaved. They are stored on-chain in an immutable fashion so that certain pieces of code can import and implement them to ensure they meet certain standards. Here's an example of how interfaces for the vault resource we defined above would look. We've got interfaces.cdc, a Cadence contract. So we've got an interface provider with a withdraw function with an amount variable and a vault resource, and then we post the result.balance is equal to amount. Withdrawal amount must be the same as the balance of the withdrawal vault. This is a check. Interface that enforces the requirement for depositing tokens into the implementing type. We've got a receiver and a provider. And so the provider has a withdraw function and the receiver has a deposit function. In our example, the vault resource would implement both of these interfaces. The interfaces ensure that specific fields and functions are present in the resource implementation and that those functions meet certain conditions before and or after execution. These interfaces can be stored on-chain and imported into other contracts or resources so that these requirements are enforced by an immutable source of truth that is not susceptible to human error. You can also see that functions and fields have a pub keyword next to them. We've explicitly defined these functions as public because all fields and functions in Cadence are private by default, meaning that the local scope can only access them. Users have to make parts of their own types explicitly public. This helps prevent types from having unintentionally public code. Okay. Enough of talking about it. We're now actually going to interact with fungible tokens in the Flow playground. Thanks for sticking with me. Let's get hands-on with this project. Now that you've read about how the fungible tokens work, we can deploy it to your account and send some transactions to interact with it. Make sure you've opened up the functional token templates in the playground by following the link at the top of the page. You should have account 0x01 open and see the code below. We do already have that open over here in our Flow playground. We have the public contract with a total supply defined. Total supply, this looks exactly the same. Click the deploy button to deploy the code. So we're going to deploy. And we just got a successful deployment. Example token is now associated with our account 0x01. The deployment stores the contract for the fungible token in your active account so that it can be imported into transactions. A contract's init function runs at contract creation and never again afterwards. In our example, this function stores an instance of the vault object with an initial balance of 30 and stores the vault minter object that you can use to mint new tokens. So we've got a total supply, and then in our init function, there it is, init. So we've got a total supply of 30. We create a new vault with a balance equal to total supply, which is 30, and then we move that resource into the vault with our self account save vault, and then we move it into our storage, and we're labeling that storage object main vault. We then create a mint and burn resource and store it to the account storage as well. So we create a vault minter and then move that to storage, and we save it. After that, we link our vault minter. We link the minter and the main minter together. This line saves a new vault object storage. Account storage is indexed with paths which consist of a domain and an identifier. Domain identifier. Only 3 domains are allowed. We talked about this in earlier lessons, but you have storage, private, and public. Storage is a place where all objects are stored, only accessible by the owner of the account. Private stores links, otherwise known as capabilities, to objects in storage, only accessible by the owner of the account. And then public is similar to APIs. It stores links to objects in storage, which is accessible by anyone in the network. Contracts have access to private auth account object of the account it's deployed to using self.account. This object has methods that can modify storage in many ways. See the account documentation for a list of all methods it can call. In this line, we call the save method to store an object in storage. The first argument is the value to store, and the second argument is the path where the value is being stored. For save, the path has to be /storage domain. We also use the vault minter object in storage in the next line in the same way. So we create a vault minter, and then we store it in our storage, and we're going to call it main minter. You should also see that the example token.vault and example token.vault minter resource objects are stored in the account storage. This will be shown in the resource box at the bottom of the screen. Now, I have not been able to find this resource section. I guess it exists, but I haven't been able to see it. I think it's an outdated part of their documentation. You're now ready to run transactions that use fungible tokens. Let's do it. Let's create, store, and publish capabilities and references to a vault. Capabilities are like pointers in other languages. They are links to an object in an account's storage and can be used to read files or call functions on the objects that they reference. They cannot move or modify the object directly. They can only use to read fields or call functions on the object that they reference. There are many different situations which you could create a capability to your fungible token vault. You might want a simple way to call methods on your vault from anywhere in a transaction. You could also send a capability that only exposes withdraw function in your vault so that others can transfer tokens for you. You could also have one that only exposes the balance interface so that others can check how many tokens you own. You could also be a function that takes a capability to a vault as an argument, borrows a reference to the capability, makes a single function call on the reference, then finishes and destroys the reference. We already use this pattern in the vault resource in the mint token function shown here. So we've got mint tokens, we've got an amount, a recipient, and then an amount and a recipient. We've got a recipient ref where we borrow. We have the optional so that if we can't borrow from that recipient, we could not borrow a receiver reference from the vault. We then get the total supply. We set the total supply equal to the total supply plus the amount that we're minting. And then in that ref, we then deposit the amount that we just minted. So when we mint tokens, which is the creation of new tokens, we check that we have a recipient, like we can actually get someone that we're sending the tokens to, that we want to mint and create those new tokens for. Then we increase the total supply of the tokens, and then we deposit those tokens into the recipient account. The function takes the capability to any resource and implements a receiver interface, borrows a reference from it, and uses the reference to call the deposit function of that resource. Let's create capabilities to your vault so that a separate account can send tokens to you. So we'll open the transaction called create link, which should contain the following code. Create link is a pretty short script. It's only got 32 lines of code. We import the example token from our 0x01 account. We then declare our transaction, prepare, and then we link our vault with our receiver and our balance. We then make it publicly accessible with the target of our vault. So we're making our vault publicly accessible as a receiver of tokens so that anyone can send us tokens. So public receiver reference created so that, hey, I'm public now. You want to send me tokens? Okay, you can send me tokens. Check that the capabilities were created correctly by getting the public capability and checking that it points to a valid vault object and implements the receiver interface. Get capability, so we check that the vault receiver reference was implemented correctly, and if it wasn't, we throw an error. In order to use a capability, we have to first create a link to that object in storage. A reference can then be created from a capability, and references cannot be stored. They need to be lost at the end of the transaction execution. This restriction is to prevent re-entrancy attacks, which are attacks where a malicious user calls into the same function over and over again before the original execution is finished. Only allowing one reference at a time for an object prevents these attacks for objects in storage. To create a capability, we use the link function. So we're linking, which creates a capability, and it's linking a public reference to our private storage. Link creates a new capability that is kept at the path in the first argument, targeting the target in the second argument. The type restriction for this link is specified within the open greater than less than. We use the and token.vault, example token.receiver, example token.balance to say that the link can be any resource as long as it implements and is cast as the receiver interface. This is the common format for describing references. You first have the and followed by the concrete type, then the interface in curly braces to ensure that it is a reference that implements that interface and only includes the fields specified in that interface. We put the capability public main receiver because we want it to be publicly accessible. The public domain of an account is accessible to anyone in the network via an account's public account object, which is fetched by using the getAccountAddress function. Next is the post phase of the transaction. The post phase is ensuring that certain conditions are met after the transaction's been executed. Here we're getting that the capability from its public path and calling its check function to ensure that the capability contains a valid link to a valid object in storage that is of the specified type. Let's test it out. We'll select 0x01 as the only signer. We'll click the send button to submit the transaction. This transaction creates a new public reference and checks that it was created correctly. Very easy, we just click the send button. Are we able to create the capability? We did, we got a successful capability created sign. Next up, so we can now create, store, and publish capabilities and references to a vault. Now we're going to talk about transferring tokens to another account. Now we're going to run a transaction that sends 10 tokens to account 0x02, but to do this by calling the withdraw function from account 0x01's vault, which creates a temporary vault object for moving the tokens, then deposits these tokens into account 0x02 by calling their deposit function. Here we encounter another safety feature that Cadence introduced. Owning tokens requires that you have a vault object stored in your account. So if anyone tries to send tokens to an account who isn't prepared to receive them, the transaction will fail. This way, Cadence protects the users if they accidentally entered the account incorrectly when sending tokens. Account 0x02 has not been set up to receive tokens, so we'll do that now. Open the transaction, set up an account, select 0x02 as the only signer, click the send button so the account can receive tokens. So if we try to transfer tokens right now, I'm just going to try this. Actually, I'm not going to jump ahead. We're just going to follow this in order. We don't want 0x01, we want 0x02. So we'll send this to set up the account for 0x02. Empty vault stored, references created. We have now set up a vault, set up an account to be able to receive tokens on account 0x02. Setup. Okay, we've got a prepare function. We've got a new vault A that creates an empty vault. We assign it to a value. We then save that vault to the account at the same path that we did in the other one. That's when we log the empty vault was stored. So we've stored an empty vault inside of that account. We then create a new receiver ref where we link the vault with a token and a balance, I believe. Yep, balance. And then we're creating that capability. The publicly accessible API is at public main receiver, and then the target, what that API accesses, is the main vault. What that's going to allow us to do is allow people to send tokens to that vault, which means reference created so that anyone can send that account tokens. We then check that the capabilities were created successfully. We check that there is that publicly accessible function. And if there is that receiver element of that public function, we're good. If not, then we say it wasn't set up correctly. Here we perform the same actions that account 0x01 did to set up its own vault, but all in one transaction. Account 0x02 is ready to start building its fortune. As you can see, when we created the vault for account 0x02, we had to create one with a balance of 0 by calling the createEmptyVault function. Resource creation is restricted to the contract where it's defined. So in this way, the Fungible Token smart contract can ensure that nobody is able to create new tokens out of thin air. As part of the initial deployment process for the example token contract, account 0x01 created a vault minter object. By using this object, the account that owns it can mint new tokens. Right now, account 0x01 owns it, so it has sole power to mint new tokens. We could have had a mint tokens function defined in the contract, but then we'd have to check the sender of the function call to make sure that they are authorized, which is not the recommended way to perform access control. As we explained before, the resource model plus capability security handles this access control for us as a built-in language construct instead of having to be defined in code. If account 0x01 wanted to authorize another transaction, if they wanted to authorize another account to mint tokens, they could either move the vault minter object to the other account or give the other account a private capability to the single vault minter. Or if they didn't want minting to be possible after deployment, they would simply mint all tokens at contract initialization and not even include the vault minter in the contract. In the next transaction, account 0x01 will mint 30 new tokens and deposit them into account 0x02's newly created vault. Select only account 0x01 as the signer and send mint tokens to mint 30 tokens for account 0x02. Mint tokens. We're now going to mint tokens. Send it. Panic could not borrow a reference to the minter. Okay. We should have already set up our account. Let's try minting the token. Oh, maybe I have the wrong account selected. We wanted 0x01. Cool. We've now minted 30 tokens and deposited them into 0x02's account. Mint tokens. Let's look at the transaction. We've got a minting ref where we take the resource vault minter. We then create a receiver where we get the capability example token.receiver. We then prepare, we get a minting ref by borrowing the storage of the main minter. If we can't get that, if it doesn't exist, then we panic, so that way we don't end up running into any errors later on. We let the recipient equal account 0x02, and then we get the capability of the public main receiver, so that way we can actually send them that. So we've set it up, we've made sure that the person calling it, aka my account 0x01, has a vault that we can mint tokens in. Then we get the account we want to send to, account 0x02, and we make sure that they have a public capability of receiver, so that when we mint tokens, we can send them to the receiver. Then after we prepared, we execute, so we mint tokens, we mint 30 tokens, and then we send them to the receiver. Pretty straightforward. Gonna wrap up this section. This is the first example of a transaction where we utilize local transaction variables that span different stages in the transaction. We declare the minting ref and receiver ref variables outside the prepare stage, but must initialize them inside of prepare. We can then use them in later stages of the transaction. In addition to borrowing references, you'll see the transaction can also borrow a reference directly from an object in storage. Borrowing a reference to the stored private minter resource. We borrow the storage, and then if we can't, here we specify the borrower and have a reference point to the private storage. The reference is borrowed optionally, so we make sure that the value isn't nil. If it is nil, the transaction will execute the code after, which is a panic, so it'll revert the print message. You can also use getAccount's built-in function to get an account's public account object. The public account object lets you get the capabilities from the public domain of an account, where the public capabilities are stored. We use the getCapability function to get the public capability from a public path, then use the borrow function on the capability to get the references from it, typed as example token.vault, example token.receiver. So we're getting the capability of the publicly accessible main receiver, and then we're checking that we can borrow, and if we can't, we panic and throw an error. In the execute phase, we simply use the reference to mint 30 tokens and deposit them into the vault of account 0x02. Okay, that is it for today. I gotta run and hop on a call, but I will be back for our next lesson in a couple seconds to finish up this lesson with checking account balances. Thank you, everyone. Hope you enjoyed the lesson. If you have any questions, please ask us so that we can help you get the answer. Thanks again. Hope you enjoyed the lesson.